but then to cock it. Okay? In a cocked position, okay, that myosin head has potential energy. When it binds to actin, it's converted to kinetic energy, energy of movement, as the thin filament is propelled inward toward the center of the A band.
Is there a way to, like, move it back, or does it just keep moving?
No, the muscle can relax. In fact, that's what we're going to go over right now. This is kind of a summary slide of what happens during muscle contraction. Here at rest, tropomyosin is covering those binding sites. So the myosin head can't attach. Now, ATP has attached to the myosin head. It's been cleaved, and that's allowed the head to assume the cocked position. But as long as the binding sites on actin are covered, cross bridges can't form. Now, when calcium is released into the sarcoplasm as a result of an action potential traveling down the T-tubule, that calcium, look what it does. It binds to the central unit of the troponin. And with that, tropomyosin is displaced. Now, for the first time, these binding sites are uncovered. So now the cocked heads of myosin are going to form a cross bridge. Okay? And as soon as the cross bridge is formed, power stroke. Okay? They're going to move the thin filaments inward toward the center of the thick filament. Once that power stroke is complete, okay, the ADP and the phosphate are released. Another ATP comes along and it binds to the head, causing detachment. Not only detachment, but as that ATP molecule is hydrolyzed, as we break that terminal bond, the myosin head then cocks again. And in the cocked position, it can, as long as those binding sites are uncovered, it will bind, and the sequence is repeated. Detachment, cocking, power stroke, detaching, cocking, power stroke. And so it creates that ratcheting movement. Now, in the meantime, there's also an active transport pump located along the membrane of the sarcoplasmic reticulum. That active transport pump is responsible for the reuptake of calcium after it's been released. Once that calcium undergoes reuptake back into the sarcoplasmic reticulum and it's no longer bound to troponin, what happens? The tropomyosin recovers the binding sites. Okay? And then muscle contraction stops. The muscle begins to relax. This is a picture now of the muscle in the relaxed position and following contraction. So this is the picture you have to draw. You can see that if this is the Z-disc defining the length of the sarcomere gets shorter with muscle contraction. The H-zone gets smaller and then disappears. Does the A-band get shorter? No, because the A-band is defined as the length of the thick filaments. That doesn't change. Will the I-bands get shorter? Yes, because there's greater overlap between the thin and the thick. Okay, one more question and we'll take a break. My question to you is simply this now. When someone dies, muscles remain contracted and stiffen. What's the mechanism? Why do patients develop rigor mortis? Does anybody know or hazard a guess?
Because of calcium?
Because the
That's like a pure yes.
ATP.
It's related to ATP. Once you're dead, you can't generate new ATP.
So you can't release and put it back in the cocked position.
So you can't detach. So the actin and myosin, those cross bridges remain attached. The muscle can't relax. But what you were saying, perhaps, is also true, is that unless you're able to use ATP to pick up that calcium and put it back in the sarcoplasmic reticulum, that's also part of the mechanism why the muscle can't relax. Okay, because in order to relax, that calcium has to undergo reuptake back into the sarcoplasmic reticulum, and that requires ATP. That's an active transport pump. So without the availability of ATP, then muscle contraction persists. Those cross bridges are maintained, so the muscle appears stiff until it begins finally to break down. So let's do this. Let's take a break now.